All right, it's time, so we'll start. So welcome to my presentation about paving the path for TrenchBoot DRTM in the Xen Hypervisor. My name is Michał Żygowski, and I'm a firmware engineer at AMD, a Poland-based company doing various firmware and Yocto stuff. You may know me from Secure Boot community. I'm a developer there, maintain Brussels SoC, PC engines, and protected platforms. I was also responsible for development of recent generation desktop support in Secure Boot. And I'm also the open parts and software technical workgroup chair. And I'm mainly interested in advanced hardware features, security, and BIOS firmware itself. A few words about what we do in AMD. So as I said, that's mainly Secure Boot. We also do some UEFI. We're also FWPD project consultants. We also do Yocto stuff. So if you are interested in any of those activities, you may also come discuss with us regarding those topics. And what I will be talking today is the never-ending dispute between the dynamic and static root of trust for measurement. Why do we even bother with DRTM? What is TrenchBoot? How does it relate to the probably well-known trusted boot, which is currently used for DRTM in Xen? And I will show explain some use case which we pursue with using TrenchBoot in Xen, which is the Qubes OS AntiAntiMate. And then I will also answer any questions. So if we talk about SRTM and DRTM, what it really is. So basically, SRTM is what we typically think about. So a UEFI Secure Boot plus some measured boot, eventually some silicon vendor root of trust, which is like rooted in the silicon itself. So example technologies like Intel BootGuard or AMD Platform Secure Boot, formerly known as hardware validated boot as well. And if we think about DRTM, it is mainly Intel Trusted Execution Technology, and for AMD it is called Secure Startup, sometimes maybe abbreviated as SKInit, as the secure instruction that is responsible for setting this DRTM. And if we have this SRTM almost in every firmware available out of the box, why we still bother with this DRTM and the whole stuff around that? So we have to first understand how SRTM complex is really. So this diagram shows the typical boot flow of UEFI firmware. And most of you probably think that the word for a machine starts at reset vector. That was probably true a couple of years ago, maybe. Nowadays, we have many coprocessors incorporated into our processors or chipsets that start its execution even before the main CPU. So they may often serve as a root of trust for our main firmware, which starts at the mentioned reset vector. So I will refer to it as a silicon vendor root of trust technology. And it is responsible for, as you can see, for securing the first instructions that run. So it is typically covering the first phases of the boot phase, so the reset vector and the very crucial platform initialization steps, which takes place in pre-EFI initialization, so in short PEI. And when we are done with the very basic initialization, the memory is already ready to be used. Then we can try to use this memory to do some more heavy operations like verification or measurements of bigger parts of the firmware and other components. So and here it will be DXE, so the driver execution environment and other stuff. So what binds those two phases, so the main BIOS and the very early boot code protected by trusted by silicon vendor root of trust technology, is the is the BIOS vendor security technology that verifies the handoff between the first phase and the second phase of initialization of the firmware. Then when we are already in the DXE phase, we can leverage the UEFI Secure Boot and all the UEFI spec security technologies it offers. And then from the last stages, we can finally boot our favorite operating system. But, excuse me? So as you can see, the chain is very long, and you can already imagine how hard it is to maintain the trust from the very beginning to the end, which the beginning we should consider the reset vector and the end possibly our target software or operating system. So the modern x86 platforms may have even over 20 various keys incorporated into this chain. So this raises concerns about for example, the event log quality from the TPM measurements, and that arises the problem of forward sealing and various software updates that will, of course, change our measurements and lead to different footprints of the software which we run. So we have to update our golden measurements which we trust, and this is often problematic if we have like hundreds of UEFI executables inside our flash chips on board. So the first element that I mentioned was the silicon vendor protection technology, which is the first obstacle and problem which is like not so friendly to open source ecosystem. Most of the utilities are often closed source, proprietary, available only under NDA, and it is often pretty hard or even impossible to implement open source equivalents. So this is one of the arguments or reasons why we should not only rely on SRTM, but also maybe look at DRTM as well. Secondly, can we trust that the hardware vendors properly configure our hardware? So the silicon vendors of trust often needs some kind of immutable space that, for example, holds our key or key hash that is used to validate against the signatures and stuff. And as you can see from this slide from Alex Microsoft, some vendors do it properly and fuse the platform, so make this key hashes or keys one-time programmable and locked, and some vendors do not. So this poses a big threat because an adversary could, for example, reconfigure your machine and fuse his own key, their own key, sorry, and basically compromise the whole static of trust for measurement and the whole chain resulting from it. Can we also trust that the keys that are fused are securely stored? Based on the recent leak from the Microstar International, it seems that we cannot even trust the vendors to keep their own secrets. So as you can see, the recent leak of the BIOS source code also leaked the private keys that were fused, which public parts were fused into the MSI products, which resulted in compromise of over 100 Intel BootGuard BPM keys, right? So basically, over 100 of the products have compromised SRTM. So basically, their trust is like 0. And yes, we also have a very famous vulnerability that was discovered in Grub called BootHall, and it is related to the UEFI Secure Boot and shim, which is the binary signed by Microsoft to allow open source operating systems like Linux and others to boot with Secure Boot enabled and default keys from Microsoft provisioned. So people sometimes make mistakes. We are not ideal. So we are unable to write perfect bugless code. And a simple buffer overflow can lead to compromising the whole trust chain and affect even millions of devices, for example, using, for example, this grab version that was affected. So what's next? BootHall v6? Well, this is another reason why SRTM is not very much practical. And all those concerns raise another question. What is the usability of SRTM? So in order to reestablish the trust, we have to reboot the device. So how often do you reboot a device? If it is a laptop, then it's probably quite often. If it is a desktop, maybe a little bit less often, but when it is a server, almost never. So how would you like to re-establish your trust in your software and system you're running? So this is where the DRTM should come into play, which, unlike SRTM, is able to re-establish the trust at almost any arbitrary point in the machine lifetime. By machine lifetime, we of course should understand the time from power on to present. And yeah, what is also in favor of DRTM is that we do not have to actually rely too much on the BIOS itself and the firmware. What we only need is firmware to actually initialize the processor to an extent that the DRTM technology and the security instructions are actually usable. The rest can be done in open source software. So what also is different from SRTM is that the root of trust is still in silicon, but is not so distant in comparison to SRTM. When we remember the diagram with the boot flow, our root of trust was like on the very beginning, nearly at the reset vector. So between the OS boot and reset vector, there were like the hundreds of the firmware modules executed. So we don't know what happened before. So DRTM gives this possibility to perform another reset, a dynamic one, and re-establish our trust right before we boot, for example, the operating system. So it gives us like another starting point for the root of trust and even lesser complexity. And this lesser complexity will make less things that can go wrong. Also, with less components to measure, we have a much simple event log, and it is much more like human readable and easier to use, for example, for the forward sealing and software updates. So how in short such DRTM boot looks like? So based on the TCG DRTM architecture specification, we have a few definitions that I will use in the following slides. So when we have the starting point of the lifetime of the machine, we have the reset vector and we have the firmware, and this everything we can like call the gap. So this is something that is unconditionally executed. It performs the preparation of the platform to boot and the software. And of course, a part of the gap may also be the OS bootloader, which can be, for example, responsible for preparing for the DRTM launch. So this preparatory environment we will call DRTM configuration environment preamble, in short, DCE preamble. So this kind of this part of software or component is responsible for the platform configuration and initiating the dynamic launch event. So this dynamic launch event is typically the security instruction implemented by the processor, which initiates the whole DRTM flow. And the execution of the dynamic launch event or initiation of such event causes the machine to enter the DCE, so the DRTM configuration environment. So it is the trust anchor that we enter, and it is responsible for measuring the target software we want to run. Typically, this DC is the most protected thing in the DRTM boot flow, and it is what is important. It is measured by the hardware. When we execute this security instruction, the hardware is actually taking this DCE, opens the TPM locality 4, and measures this blob into DRTM PCRs. And when it is done, the controllers hand off to the DCE, and DCE is then instructed to measure our target software based on the parameters. For example, we have feed it inside the preamble, and then after the measurement is done, the execution is handed off to our target software. In this case, the nomenclature says it is a dynamically launched measured environment. So this is the target software or application we want to ultimately run. What is also very important in DRTM is that it does not reuse the same registers in TPM to store the measurements. So we have like two separate words. SRTM uses, for example, the registers from 0 to 15, and then the DRTM uses PCRs, so those measurement registers from 17 to 22. And also another important thing is that those PCRs, 17 to 22, are locked prior to the dynamic launch event. So it is impossible by the BIOS to actually store any measurements in those registers before the dynamic launch event is invoked. So the whole DRTM technology can be implemented, for example, using a TrenchBoot project. So TrenchBoot is a framework that allows individuals and projects to build such security engines, for example, to perform the launch integrity actions for their systems, using, for example, the DRTM. And it builds upon those technologies to establish one or more root of trust, from which a degree of confidence that integrity actions were not subverted is derived. So the first implementation of DRTM by the TrenchBoot project was done for grep and Linux. So what now we want to do is to extend this to Xen. So a little bit of recap what we have now regarding the DRTM and Xen. So currently the available implementation is made by TrenchBoot. It is a reference implementation from Intel for their DRTM technology called Intel Trusted Execution Technology. But as it is only Intel, there is no AMD support, of course. So that is one drawback from the TrenchBoot compared to TrenchBoot. In TrenchBoot, we try to cover multiple silicon vendors as well as multiple architectures. So the first goal in our project or work was to replace the trusted boot with TrenchBoot implementation, and possibly open a way to enable AMD platforms to benefit from dynamic launching as an hypervisor as well. So our use case is to support the Qubes OS AntiAntiMate application using this DRTM launch. AntiAntiMate is a set of software or scripts that help users to ascertain that his or their platform was not tampered with. And it leverages the DRTM and the measurements it makes of the software to make those statements that machine is not compromised. It also additionally uses the .p codes and other various time-based passwords and additional secrets stored on separate medias to ensure the best possible security and ascertaining the platform state. So currently the support only covers Intel TXT with TPM 1.2 and legacy boot mode, so it is very, very limited. As we try to expand it to TPM 2.0 and of course the AMD as well. So what our efforts were up to this point. So the main goal for the first stage of the project was to replace the trusted boot exokernel from the DRTM BootHall in the Xen Hypervisor, and implement a native code that will handle everything what tboot did actually. Additionally, we are also implementing the TPM code that will be used to measure the DOM0 kernel and initial RAM disk to the TPMs when we detect dynamic launch. We also had to implement the special core bring up that is necessary after the dynamic launch, because as I mentioned, the DRTM is also a kind of reset that places the CPUs in a special state, and before actually Xen can start initializing the CPUs, a special waking up from the dynamic launch needs to be performed before Xen can actually start touching the CPUs in their standard routines. We also extended the grab bootloader multi-boot module to serve as the DCE preamble, so it prepares the CPUs and invokes the dynamic launch event just to start the DRTM boot flow with Xen Hypervisor. So our ongoing efforts include preparing the proof of concept patches for upstream to XenDevil mailing list. We are still extending the Qubes OS AntiAntiMate scripts with TPM 2.0 support, and we are also going to integrate the AMD DRTM support in Qubes OS packages. And the whole effort was sponsored by lnnet Foundation, which is like very, very huge help to TrenchBoot project, and allowed us to move this effort forward. For interested people, please refer to Qubes OS patches under those links. You can find also more details on the project on those sites. So I will just shortly describe how our stack looks like. So for DCE preamble, we use grab, as I mentioned. The RFC patches were actually already sent quite some time ago to the grab devil mailing list, but now they need some updates because it was like a few years ago. We are working on a slightly modified boot flow for the Linux kernel, because apparently Linux kernel is very concerned about the UEFI and the secure boot, so they want to have control over the exit boot services call. So you had to like modify our approach to booting the Linux kernel with DRTM, and it also a little bit affects how we are approaching it for Xen. So what actually grab does is everything that is described in the following specifications. So in Intel TXT, it does the what is specified in the measure launch environment developers guide, and for AMD it does what is described in the AMD 64 architecture programmers manual. So in short, it just prepares the CPUs and the TPM for the dynamic launch event. So there are some specific requirements about the TPM state and the CPU state before the DRTM can be initiated. For Intel, it does also set up necessary structures in the memory, so addresses of the software which is supposed to be measured, where is event log to be found, and other stuff. And for AMD, it is like preparing the secure loader. The secure loader is the DCE for AMD, and it's also filling the boot parameters into the secure loader. So it also has to tell which software to measure and how to boot actually the target software. And we also extended the grab relocator to actually invoke the dynamic launch event and jump to the DCE with equivalent secure instructions. So a little bit about what DCE is. So DCE is the first component that is actually measured in the DRTM boot flow. In case of Intel, it is authenticated code module. So it is a small blob of code that is signed by Intel, and is verified by the CPU microcode. And it does the measurements of the dynamic launch measured environment. And in the case of AMD, it is called Secure Loader. And thankfully to open source community, it was left to developers as an exercise to implement that. And the architecture developers manual actually explains everything how to implement that. And we actually did it. The source code is accessible on the TrenchBoot GitHub. And we called it the Secure Kernel Loader, formerly Landing Zone. Do not mistake with Skylake, because the shortcut is the same. And the DCE is measured, as I mentioned, by the hardware, by sending the DCE blob to the TPM by the means of the TPM hash start, hash data, and hash end in the TPM locality 4. And what is most important, the DLME. So the DLME in our case is the Xen Hypervisor. What we needed to do in Xen Hypervisor, for example, to make it be launched by Intel TXT, is a measure launched environment header. So it is Intel TXT specific structure described in the TXT specification, which I mentioned earlier. And we also had to add the TPM code that is responsible for measuring the DDoM0. We also added code to extend the event log, which is provided by the DRTM. And as I mentioned, we also needed to implement the special CPU wake up because the DCE left the CPUs in a special state that requires specialized routines to actually wake them up. So before Xen can actually start using the CPUs with its standard routines, it has to perform this wake up and restore some registers that were saved before invoking the DRT dynamic launch event. And yes, and we also replace all the activities that were implemented for T-boot, the trusted boot. So we are like reserving those Intel TXT specific memory spaces, search for the event log, etc. and etc. And of course, restoring MTRRs and MSRs that were saved before the dynamic launch event. Okay. At the end, I would like to send a big thanks to people that contribute to TrenchBoot, that were developing the solution. So it is Daniel P. Smith, Andrew Cooper, Daniel Cooper from Grab, Christian Habel, my colleague from FreeMDAP, and Ross Philipson. And yeah, I'm open for questions. We still have some small time. Yes, please.
What happens to SMM mode code in? Yeah, just talk so people can listen.
One question, what happens to SMM mode code after the DRTM launch? Where is that measured?
Okay, so that's a good question. So firstly, after dynamic launch, the SMM interrupts are actually inhibited. So it is supposed to give the target software time to set everything properly up before the SMM can be started again. And Intel TXT actually provides a way to measure the SMM. Previously, it was called the SMM transfer monitor. SMI transfer monitor, not SMM. Okay. It was a small hypervisor inside SMM that installed. That when installed, it caused the first VMX instruction that was like invoked caused the VM exit and caused the installation of SMI transfer monitor, and also DRTM had a field to fill information about the SMI transfer monitor. So DRTM could actually measure the SMM transfer monitor during the dynamic launch, which actually allows us to have some kind of footprint of SMM, because SMI transfer monitor also has kind of descriptors of SMI handlers, so which resources given SMI handler may use, and the hypervisor actually controls whether given SMI handler does not try to go overboard and try to access any other resources. So by measuring the SMI transfer monitor, we could get a glimpse of what is inside SMM and how it works. Any other questions? Yeah, please.
In similar spirit, what's about UEFI runtime services?
Okay, so I had something about UEFI in the backup, but the time didn't allow me to say anything about it, unfortunately. Regarding the UEFI, so our plans were to actually avoid UEFI at all costs. So, but we wanted to still implement the support for DRTM launch for the native PE42 entry point, so that people that still insist on using UEFI Secure Boot could still verify the image when loading it and still perform the dynamic launch when the image is already loaded into memory and jumped into from the DCE. Regarding the runtime services, there is actually very little use of any services from UEFI in Xen, actually. There's very, very little information that is taken from boot services, actually, and runtime services are, I think, almost unused at all. So it is only kept for DOM0 for eventual use. And additionally, Xen has a command line parameter that can stop exposing the runtime services to the DOM0. So basically, with some small effort, we can actually get rid of accessing UEFI at all from the multi-boot entry point. Any other questions?
Someone has to access UEFI, I guess, to get the memory map and things like that?
Yeah, sort of. Memory map, some frame buffer information if it wants to display some debug logs on VGA. What else? Boot device, I think it was also the case. And of course, doing exit boot services, I think it was the reason why Xen still had to access the UEFI stuff. But we can also make the exit boot services call right before the dynamic launch event, and this is what I think we plan to do when using the multi-boot entry point.
For non-zero use, specifically get variable and set variable are.
Yes, this is from the runtime service, exactly. Well, if you need to actually save something in the variables, then you will probably need the runtime services. But what Linux have I use from the runtime services and the variables. Most probably, if we want to reboot to the firmware setup, this is setting the variable called OS indications, I think. But besides that, this is just, I think, arbitrary writing to variables that one may do using FIVRFS or something like that. But besides that, I don't see much use from Linux regarding the UEFI variables.
Modifying boot order, but
Yeah, of course, as well.
but also if you're non-zero kernel panic, there is a way to save kernel lock into FI variables.
Okay, that makes sense.
Useful on some systems.
Well, I leave to the end users to pass additional parameter to Xen kernel command line to disable runtime services or enable it whenever necessary. That's just a toggle flag, I would say so.
I guess this boils down to do you trust the set variable, get variable implementation of a BIOS vendor?
That's also true.
Yeah. If you trust, then you can use and you can enable it and expose to the system. And if you don't trust,
Yes, it all comes to the trust, and we want to trust in DRTM, not the BIOS.
Maybe the code could be measured.
that's a good question.
Or maybe it can be sandboxes somehow,
Yeah.
like running not
So-
using zero, but
Okay.
I think we're over time.
Yep, exactly. I'm open to discussions also in the breaks, so I'm sorry, Andrew, for taking your precious time. I hope you don't mind. Thank you.